For today's webinar, we have David Witzke presenting Image Quality and Clarity, the Keys to Forensic Digital Imaging Processing. Without further delay, here's David.
Ladies and gentlemen, the class that we're going to be talking about today is called Image Quality and Clarity. There are a number of key components to the digital imaging process, but even before you can start the imaging process, you have to have an understanding as to what it is or what is required in order to do an accurate and reliable analysis and comparison. And that also gets into the process of digitally enhancing your images. So when we get into the digital imaging process, we have two types of analysis that we are generally concerned with. One is the cognitive image analysis, which is the visual examination interpretation of the actual image data. Now, this is where we get into the process that is probably commonly referred to as subjective analysis. A lot of people also refer to this as scientific analysis, especially when we're getting into forensic disciplines. Now, the only problem with cognitive image analysis is that this is something that is subjective because of the fact that it is how you interpret the data, and that can have many different meanings depending upon whether or not, as the old saying goes, are you having a good hair day or a bad hair day? We get into the quantitative image analysis, and this is something that uses actual measurable data. Now, when we get into image authentication, image verification, we have certain types of components that we are concerned with in terms of being able to actually validate the image as to whether it is a true and accurate and reliable image. But in terms of part of our image analysis, we have other things that we have to take into account. This is where we get into things such as resolution. How much resolution is required for the ability to visualize the detail clearly, or how much color or contrast is available so that you can actually visualize the detail accurately. So this, again, is something that is measurable, and it takes the subjectivity out of it and makes it a totally objective process. There's one problem that we get into, especially when we're dealing with certain disciplines, especially things such as trace evidence, where we get into footwear or tire tread, because the quantitative image analysis does not consider distortion issues. And one of the greatest problems that we have within the photographing of footwear or tire tread is perspective distortion. And that has proven to be a huge problem, even when we try to do things such as calibrating our images or making sure that the images are in focus, or whether or not we can actually analyze the characteristics or the details that are contained within the image. So when we're starting to talk about what is required for this process of digital imaging analysis, we have to make sure that we are using the appropriate type of camera. Now, there are a couple of different standards bodies that are writing standards for trace evidence footwear, and they are, I guess the best way of putting it, their idea is to lower the bar to the lowest common denominator so that anyone who may have a camera can actually photograph trace evidence. The problem that I have with that is that they do not always take into account what is best practice or what is the best technology. For example, one of the requirements that we have is to have a digital single lens reflex or DSLR camera. This must have interchangeable lenses. You cannot use a camera that has a fixed lens. Also, something that is not discussed in the standards because of the fact that they say it is a cost issue and there has been some concern about whether or not it has been analyzed subjectively in terms of the data, in terms of verifying and validating it, as to whether or not you actually need to have a full frame imaging sensor. And my guideline, my recommendation is that you must have a full frame imaging sensor. There have been enough studies that have been done within the field of photography since using digital cameras that we know beyond a reasonable doubt that a full frame imaging sensor is going to give you better quality images. The smaller the sensors, they're more prone to noise and other distortion issues. Also, when you're trying to capture things, you want to make sure that you are using a macro lens, something that has a flat field so that you do not have curvatures or lens or barrel distortion issues. And something that you should also have are polarizing filters, and we also recommend that you have interchangeable photographic camera barrier filters, such as your red, orange, yellow, depending upon the type of alternate light source that you are using. And of course, you want to make sure that you have a copy stand so that you can properly balance not only maybe you're dealing with a lift of a footwear impression, maybe you've got a static lifter, or maybe you've got a casting, or maybe you've got a shoe that was obtained from the suspect. So you want to have something where you can actually stabilize it so that you are getting good photography. So when we get into understanding a little bit better about what is the difference between cognitive image analysis and quantitative image analysis, I want you to look at the blocks in this illustration that are labeled A and B. These two blocks appear to be very different color values. And when we start looking at the color values, we need to be able to do an analysis, a quantitative analysis of those colors so that we can make an appropriate assessment of the type of image that we're dealing with. Is there distortion? What are some of the other issues that are going on? So one of the things that we get into is, in order to do this process, I want to go ahead and open up this image. And again, we have the blocks that are A and B, and they appear to be, again, very distinct colors. Now, when we're talking about colorimetry, we're talking about bit depth, and we're talking about the numbers of pixels that make up these different values. So in order to assess the color values, one of the things that we can do in Photoshop is we can use this thing called a color picker. Now, we can actually set it up so that we have our foreground colors, our background colors, and what we're dealing with, we're going to be dealing with our foreground colors. But in order to illustrate how this works, I'm going to position my cursor on the top of the green cylinder. I'm going to click and release my mouse button. Now, once I have my cursor at that location and I click on that color value, it will show you precisely what that color value is in terms of color details or colorimetric data. In terms of hue, saturation, and brightness, we also have red, green, and blue values. We also have lab color, which is something that is specific and unique to digital technologies. And then we also have the CMYK. Your CMYK is generally considered your output. Now, under certain conditions, there are things that we can do to take advantage of CMYK colors during image processing, but that's a story for another time. The thing that I want to focus on for the moment is this thing called brightness, because again, that is the brightness or the intensity of the light that is reflected from the object. And then we have the red, the green, and the blue values that are used that contribute to, or the mix that contributes to make up that particular color value. Now, again, if I go to another location on my screen and I click and release my mouse button, you can see that my brightness value and my red, green, and blue values have also changed. And I have a hexadecimal value, which this allows me to itemize or to identify a singular color value out of 16.7 million different color values. So as I'm going through this process, again, I can just move around and you can see how those numbers change. Now, I want to do something so that you can see that I'm not doing anything fun or doing something untoward, so to speak. I'm going to click on the background. So now my background is white. You can see this color value for white. And I have a brightness of 100%, very bright. And I have an RGB value, or red, green, and blue values, each with 255, 255, 255, or my hexadecimal value is FFFFFF. So that's how I can identify that particular shade of white, or that particular shade of gray, I should say more accurately. Now, I'm going to position my cursor over on the letter A, and I'm going to click and release my mouse button. So on my brightness value, I have a brightness of 47%. I have a red, green, and blue value of 120, 120, 120, or a hex value of 787878. So again, I can see exact numbers or an exact identification for that colorimetric value. Now, if I were to go over and go back onto the green cylinder, I just want to do this just so that you can make sure that I have in fact changed the color values. Again, you see that I've got all sorts of totally different values throughout. And now I'm going to position my cursor back over on the letter B. And once I get to the letter B, I'm going to click and release my mouse button. Now, how interesting. I have a brightness value of 47%. I have a red, a green, and a blue value that is 120, 120, 120, and a hex value of 787878. Well, now wait a minute. That was the same value that I had for the color block A. How can this grayscale value and this grayscale value for the letter B, how can they be that identical and yet have such a visual distortion in terms of looking like they are two totally separate, different color values? Now, this is something that we encounter in trace evidence a lot because of the fact that we have a number of other issues or other items, if you will, that impair our ability to get a good photograph. We can have the different types of lighting conditions. We could have a problem with shadows. We could have all sorts of different issues. So when we stop and talk about it, if you'll notice that the light is coming in from the right side of the cylinder, and the light is striking this right side of the cylinder, which is why it is so light, that as the light is blocked on the backside of the cylinder, it becomes very dark. And so you'll notice then that we have this distortion that is caused by the shadow. So let's take a little bit of a different look at this. I'm going to make a little square here by the letter A. I'm going to get the move tool and I'm going to just slide it off. And so you can see that I've got a nice dark gray there. But if I start coming down across that white block, and once I get down into the area where you can actually see the shadow of the cylinder, notice how it even starts to change colors. And then by the time I actually get it down into the location in the block, or in the block where the letter B appears, that even if I were to turn off the marching ants, you can't even see the difference as to what pixels I moved and where they're even located. So again, that's where they are. Turning them or putting it back, you can again see where I've got the different shade and it looks totally different. So when we're getting into understanding the difference between your cognitive understanding or your cognitive appraisal or your cognitive opinion based upon your analysis, you have to take into account things such as distortion. And once again, when you're dealing with trace evidence that may be on a static lifter, or maybe you've got something that was photographed in place, or whatever the case may be, you do have to take time to actually understand and evaluate both the actual resolution, how many pixels do we have sufficiency for resolution, and what about the quantitative? What about the colorimetric values? How is that going to affect you? So as we go back into talk about this process, we want to make sure that we are, again, understanding the difference or differences between perception as well as fact. Now, when we're talking about these different perceptions and different facts, we have some key words that we must understand to help us to explain this technology. So we get into resolution, we get into the bits, the bytes, the kilobytes, megabytes, gigabytes, etc., and we get into pixels per inch. Now, as we are looking at these different size imaging sensors, we also have to get into other facts that are going to affect how accurately we can, again, capture the detail. What does that do to the focal length multiplier? How does that affect the area or the size of the area that we are capturing with that particular sensor? So we have to then make sure we understand that there are components that are going to cause, again, interactions on both planes, cognitive as well as quantitative. And so we then have to make sure, again, that we understand things such as the distance between the object and the lens when we're capturing larger items, because that's going to get into lower resolution and lower image quality. So when we're getting into the resolution understanding, this is where sufficiency comes in. What is sufficiency of resolution? We have level 2 or level 3 detail and latent fingerprints, but we also have different types of artifacts and trace evidence, whether it's footwear or tire tread impression. So we have to make sure that we have sufficient resolution that we can clearly identify the type of artifact or the characteristic. Just to sort of give you a quick view, I'm using fingerprints on this because with fingerprints, it's really a very simple process when we start talking about sufficiency. Starting over on the left, I have sufficiency because I can see the rich detail going across this dark background. I can see the rich detail, I can see the furrow, and I can see that separation clearly. And there's a difference in the contrast between the ridges and the background. In the middle image, I have sufficiency of resolution. There's separation of the detail, but because of the bit depth or the color, I am starting to lose the ability to visualize that level of detail accurately and reliably. So while I may have sufficiency of resolution, I don't necessarily have sufficiency of bit depth. I would like to have more contrast. The image over on the right, you can see that, again, I have probably sufficiency of resolution, but the contrast, the level of detail between the ridges and the background, there's absolutely no way that you can distinguish that. So this is where we get into, again, the issues as far as bit depth are concerned and sufficiency of bit depth. So as we look at this, we need to take into account what is the resolution of the camera? Do we have sufficient resolution or high enough resolution for the camera to actually get that level of detail? What is the sensitivity of the bit depth of the camera? This is where we get into 12, 14-bit bit depth. Again, we also have the size of the imaging sensor, which is going to adjust the closeness or the proximity to the image, which is going to affect how clearly you can see it. And again, we want to make sure that we can get the camera as close to the object as is possible for the appropriate contrast. When we get into, again, just standard 8 bits, we are talking about a bit value. You've got 8 bits, and each bit can be either a 1 or a 0. And so when we put this together, that for the first bit, I have 2 colors or 2 shades of gray, black or white. And then if I add another bit, that's going to double those options. And I can continue to double that until I get all the way out to 8 bits, which is going to give me 256 shades of gray. Now, as we're talking about the different bit depth, we need to understand that technology is a great tool and that we are going to have a high degree of sensitivity. And this is crucial when trying to photograph trace evidence. When we get into 8 bits, again, we have 256 shades. 10 bits, we get into 1024. 12 bits, 4096. 14 bits is where we get into 16,384 different shades. Almost every commercial camera, digital camera that is available today is going to give you the option of doing 14 bits. And so at the point of capture, you can actually have a higher degree of sensitivity than what you can when you're actually doing the processing. So this is where we get into understanding what types of file formats that we're going to be dealing with. And it's one of the reasons why you should be using a camera raw file format, especially for trace evidence, because of this high degree of sensitivity. This degree of sensitivity is commonly referred to as HDR, or high dynamic range. And again, that's going to affect how well we visualize that data. And it's also going to help us in assessing the number of shades that we have of red, green, or blue. Or if I've got grayscale, I've got 8 bits or 1 byte of data for each pixel. So if it's 24 bits, then a color image is going to have 3 bytes of data for each individual pixel. So the size of the imaging sensor, the number of megapixels, does have a rather important bearing on you. Now, when we get into our HDR situations, our high dynamic range environments, that they're actually, even though it's only captured at 14 bits, because of the way in which a Microsoft Windows environment or even a Mac environment, that it's based upon 8 bits to a byte. So in other words, if we're using 14 bits, then we're going to have 65,000 shades of red, or 2 bytes of data for each pixel. We have 16 bits or 65,000 shades of green, or again 2 bytes, or 16 bits or 65,000 excess of shades of blue. So the bottom line is that when we're capturing these HDR values, these high dynamic range images, these can be very large files. So we need to also consider how many files we are going to have when we're going through this process, because we can exceed our storage capacity very quickly. Now, again, when we start talking about the dynamic range, color values are expressed based upon a light spectrum that ranges from a visible range to an invisible range. But then also we have another component, which this is our grayscale value, also known as the brightness value. So again, the ability to have contrast separation is what's going to give us the ability to visualize the clarity within that image. So we have to, again, make sure that we are talking about the appropriate number of pixels as well as the appropriate bit depth. So when we're talking about the number of pixels and we're trying to get that separation, that distance from lens to object is extremely important, because when you think about increasing the amount of data for a single pixel, that if I were to double that to capture an area that is twice as large, I actually have the original ratio, or the area ratio for my original pixel is actually 4:1, because I have my 1 pixel, but I've doubled it horizontally, but I also have to double it vertically. And so because pixels are square, you can see that that 1 pixel, that's 1:1. At just expanding it twice or doubling the resolution, then I'm going to have a value that is going to be 4 times larger. And then again, to expand that out even further, when we get out into something that's 4 times as large, I've got 4 pixels horizontally, 4 pixels vertically, making it into a square that's 16. So when we actually start talking about the difference of the size of the area that we are covering, we have to think about how many pixels do we have to capture that area. Because when we get into, again, being able to visualize the detail, we have to think about how many pixels do we have on our image, and how many pixels do we have on our monitor, or how can we visualize that level of detail on the monitor. Now, again, this is all going to get into the issue of sufficiency. So again, to go back to Photoshop, when I have a test target that I'm using, and if I'm trying to zoom in, I want to be able to see the level of detail so that I can see all of my individual line pairs. Again, this is where we get into our quantitative analysis. There is no subjectivity in this. Now, if I start zooming out and all of a sudden you start seeing that my detail that I'm seeing on my screen, I'm actually losing line pairs. So I'm losing the ability to do an accurate analysis of that image. So we have to be considerate of what we are doing when we zoom in or zoom out on our images. And again, that has to do with the resolution at capture and what is the calibrated resolution for your particular items. Now, when we get into this issue of understanding how this process is going to work, we also have to understand what resampling means. And the resampling process is where it breaks it down into individual pixels, and we either discard known pixel values or we add or insert for interpolation, we add in values that, as I like to say, that come from MSU, which is making stuff up. So we have to always take into account what happens even when we are simply analyzing the data on the screen. And especially for trace evidence, you should be making sure that you are looking at this level of detail at a 1-to-1 value. So again, just to show you how this actually looks enlarged, that this was the screenshot that I was showing you earlier in life, but as you can see that in resampling, that my detail here on the left, it has been resampled, and so I have lost detail. Now, if I'm looking for certain types of characteristics, that I have to be very careful as to how much resampling is being done. I want to always make sure that I can zoom in to 100% so that I can accurately visualize the detail so that I'm making the appropriate and most accurate and reliable assessment based upon the actual quantitative values and not just simply dealing with something for an invalid cognitive assessment. So again, when you start talking about the sufficiency, we have to make sure that we are talking about the appropriate terminologies. We have a difference between pixels and dots. Pixels are used to measure image quality or resolution when it is stored or displayed on a monitor or when it is printed. Now, the characteristics of pixels, pixels are square. A pixel can be one of up to 256 different possible shades of gray, or one of 16.7 million different color values. In other words, 256 red times 256 green times 256 blue, which is where you get your 16.7 million different color values. Also, pixels are continuous tone, so there is no white space that separates the pixel color values. When we get into dots, now again, I'm hoping that very few of you are actually printing out any type of trace evidence, because printing is the most destructive process that you could ever possibly use when it comes to dealing with trace evidence. First off, dots are round, but it depends upon the type of paper and the type of ink that you're using, how much of the ink bleeds into the paper. Also, dots work with white space or the white paper to simulate a color value. And a dot has only one single color value. A black and white laser has only one color of toner to simulate 256 shades of gray. So how do you get 256 shades of gray with only one color toner? You don't. If you're dealing with a CMYK laser printer or an inkjet printer, you typically only have 4 colors. So a dot can either be cyan, it can be magenta, it can be yellow, or it can be black. Problem is that when we are trying to come up with something that is a teal background, or maybe it's even a red background, how do you represent that when you do not even have that color shade as far as your colors of dots are concerned? So the problem is that when we are dealing with dots, dots are very subjective, and we are limited to the amount of information that we can represent. Now, what that simply means when we're dealing with a black and white laser printer is that we get into something that's commonly referred to as a 4x4 dot pitch grid. So in other words, we have a grid that is 4 dots horizontal by 4 dots vertical, and every time we fill in one of these spaces, that's going to give us a different shade of gray. So if we have 4 dots filled in, that's going to be a shade 5, because we can leave it blank, and that's shade 1. And so we've got 1, 2, 3, 4, so 4 plus 1 is 5. Or if we have 8 cells, we've got our different shades. Again, this is going to limit the number of shades of gray. Bottom line is that we are restricted to only 17 shades of gray when using a standard black and white laser printer. Black and white laser printers should never, ever be used for anything trace evidence. Just to give you an idea, these are the 17 different shades of gray that a printer can print with the number of dots. And you can see that if you have a color value that is close to 204, but actually has a value that is closer to 187, I could have a characteristic on my footwear impression that is going to be represented by the same pattern of dots as the background. So I lose the ability to visualize and distinguish between that level of detail. So you have to make sure that you have sufficient contrast when you are going to be dealing with your images in the event that you should have to print them. But once again, we are trying to get people away from this idea of printing. So if you are going to do printing, do not use a black and white laser printer. You want to use an inkjet printer, and you want to make sure that it has a sufficiency in terms of the numbers of dots that appear within the print head. So we have a number of different values as to how we can actually calculate how much detail is lost versus how much detail is actually present when we're doing something such as printing. So again, please be cautious and please be careful when considering to print. We have the different types of printers. You've got, again, different types of inks. The thing to remember is that you want to use an inkjet printer that has higher or more ink color values. And so you also want to make sure that you are using a high quality premium photo glossy paper so that the dots are blended together and so that you can actually see a more accurate representation of those values. So just to give you an idea, when we get into the different sizes of picoliters, which just simply means how many dots are there that are being printed on our single pages, then you can see that we actually get into a different set of dots or different numbers of dots, even within the same grid, even using a standard 4-dot pitch grid. So just to show you the difference in terms of how that looks on output, we have the actual test target. This is the value that was printed. We have different dye sublimation printers that were output. And over on the bottom left, that is an inkjet printer. The output over on the far bottom right was actually a black and white laser printer. So you can see then that trying to print something can actually degrade the quality of your image, and you want to be certain that you're using the appropriate type of technology. And again, I want you to always ask yourself, is printing even relevant? Again, I want to go back to my original statement up in the beginning. When we're dealing with forensic digital imaging, we are talking about what is required for the sufficiency in terms of being able to do an accurate and reliable cognitive assessment, as well as what is the quality or the level of detail from a quantitative standpoint, so that you can make an accurate and educated assessment analysis of the evidence. So again, ladies and gentlemen, I want you to always think in terms of those two components, because it's always going to be about making that accurate and reliable analysis, comparison, and evaluation. Thank you very much.
All right. Thank you, David, for such a fantastic, informative presentation. Let's go ahead and get right into some questions from the audience. Go ahead and I'm going to go ahead and dive into this one since it was the most recent, the last topic that you covered. Somebody in the audience asked, what's your opinion on using a dye sublimation printer?
I'm not in favor of dye sublimation printers, primarily because of the fact that even though they may claim to be high resolution, they are actually very limited in the number of pixels that they are actually representing, based upon the way in which the dye is actually melted onto the paper.
Understood. Generally, again, like you had mentioned, that avoidance of printing as much as possible and only as a last resort seems to be the best approach.
That is absolutely correct. One of the other things that we get into within dye sublimation printers is that they have, we've actually observed a loss of image quality when printing, but because of the fact that they are considered to be photorealistic type printers, that it causes an unacceptable or unreliable assessment of the image. And again, that's caused a few problems when we've been in court with images that have been printed on dye sublimation printers.
Gotcha. Real quick, just to make sure, because we did see a couple of people in the audience ask questions related to what program you were using and what you were showing in your presentation. And if I remember correctly, that is Photoshop. And what version of Photoshop were you using?
Everything that we are doing right now is Adobe Photoshop CC version 2021.
Okay. So yeah, so just for everyone in the audience, that is your point of reference for anything that you saw during the presentation. That was it was Adobe Photoshop, and the version was the most recent version. Another question I have here: why capture images? Why capture images in Camera Raw, aka HDR, if Adobe Photoshop only provides options for processing 256 shades per channel?
When we're actually capturing our images in a Camera Raw file format, the data is actually preserved in its full dynamic range. When we're using the Camera Raw converter, we're actually reading the raw data. The image has not actually been converted into an image format at that point. So we actually do have the ability to visualize data at a higher bit depth when we're processing it and when we are trying to do our initial assessment, when we are viewing images in the camera raw converter. Now, once we have converted the data into an image format and it's opened up into Adobe Photoshop, anything that you use, whether it's levels, curves, shadows, highlights, etc., everything is based upon a value of 256 shades per pixel value. If it's grayscale, that means you have 256 shades of gray. If it's in a color value, then we are looking at having 256 different gradations of red, green, and blue. So I guess the bottom line to sort of summarize that is when we're dealing with the camera raw converter, at the initial outset, we can actually optimize our starting point for when we are trying to do things in the actual physical processing, such as suppressing background noise, creating additional contrast, etc. So that will always give you the highest possible separation of detail.
Understood. Do you have any tips on Photoshop, using Photoshop to resize images one for one?
Yes, there are two different techniques for calibrating images. In the Adobe Photoshop, the process or the technique that we use for anything trace evidence is a calibration tool or a calibration process known as the cropping method. When we're dealing with the cropping method, it helps us to identify those other types of distortion, perspective distortions. And so if you've got something where you can visualize whether or not something was focused at an angle where the copy or where the camera lens may not have been exactly perpendicular to the impression, i.e. the footwear. And we see this a lot where our footwear impressions take on almost a trapezoidal effect based upon the distortion or the angle of the camera in relationship to the item being photographed. I cannot stress the urgency enough about being able to capture your images where the image plane, the imaging sensor, is parallel to the item that is being photographed. That is extremely crucial.
Another question I have here, and it's kind of related actually with resolutions and using Photoshop. Is there a minimum resolution that be required for trace evidence such as footwear impressions? And this is a little bit of a two-parter. If there is a minimum resolution, what is the recommended? And if there is no standard, why isn't there a standard?
That is such an excellent question. That is probably the number one question of the day as it pertains to not just simply trace evidence, but to a lot of disciplines. When we are dealing with sufficiency, there is a false narrative, I guess is the best way of putting it, where the latent print community has a quote standard for a minimum resolution of 1000 pixels per inch. That has very little, if anything, to do with sufficiency of image quality. The 1000 pixel per inch standard actually is based upon an APHIS standard, so that if you have two fingerprints, that as long as they are the same resolution, you can accurately match up or align characteristics such as an ending ridge, bifurcation, etc. So that is somewhat of a misnomer in terms of having a standard. In terms of the OSACs, there has not been a research. As a matter of fact, prior to my departure from OSAC, I was actually on a subcommittee where we were trying to get a research and development process so that there would be a study being done of what is sufficiency in terms of resolution. Again, for most trace evidence or footwear impressions, we are looking at usually 200 and maybe 250 pixels per inch, 300 pixels per inch. But it's also, again, based upon the size of the area that is being photographed, and people want to try to photograph the entire object as it exists in one sitting. The problem is that when we're trying to zoom in and look at these different characteristics, as we start to zoom in, the lower the resolution, the lower the calibrated resolution, the more that we are going to encounter a problem of pixelation as we zoom in. So that's where we get into the correspondence between what is the resolution of the sensor in the camera, what is the calibrated resolution, and how much can you zoom in on your monitor? What is the resolution of your monitor? Where does that sufficiency start to fall apart? We need to do a lot more research in this area in forensic disciplines, especially footwear. Footwear has historically been a bit problematic in that we have not had the amount of research put into certain areas because, again, lack of understanding, lack of attitudes, etc. But again, as far as having a higher resolution, the higher the resolution, the better the quality of the image, the better the ability, the better you have the ability to visualize characteristics within a footwear impression, whether it be a wear pattern, whether it be a crack in the shoe, whether it be even a pebble that is embedded within the actual tread on the footwear. So there are a number of things that we can do to help improve the visualization of that. And that's by either taking an overall photograph of the entire object and then taking close-ups of individual areas so that we get a sufficiently higher resolution so that we can clearly see those characteristics. I've got a couple of examples of those types of items in the lecture on Thursday.
Awesome, thank you. And I'm glad that you made mention of OSAC, because that is actually another question that came up, was asking if there was any an OSAC or any other best practice resource currently available for the comparison of digital image evidence. So I'm glad that you covered that.
Yes, there are two different groups within OSAC that are dealing with photographic imaging of trace evidence such as footwear. There's the footwear OSAC group, and then there's also a group called VITAL, which is the video and imaging analysis group. So those are the two groups that are actually looking at this specific area.
Thank you. Another question I have here is the amount of noise offset with a high resolution APS-C imaging sensor versus a lower resolution APS-C imaging sensor.
Yes, as I alluded to in the session, that there are two different frame sizes or imaging sensor sizes that are common in most digital cameras that have interchangeable lenses. One is a full frame imaging sensor, which is the size of a standard frame when we were talking about 35 millimeter frames, which is 36 36 by 24 millimeters, which gives us 35 millimeters diagonally. The smaller the imaging sensor, when we get into the APS-C imaging sensors, there are actually two different variations on that. One is a Canon model or Canon variation, and the other one is a Nikon or other size or variation. The Canon APS-C is actually smaller than Nikon. And when we get into the different issues in terms of the sizes of the sensors, that will affect the size of the photoreceptors that are used to capture data. There have been hundreds of studies with different cameras, and it is a very well-known fact that when you get into a smaller frame or a smaller sensor, you have smaller photoreceptors. So that means you're going to be picking up a lot more noise or a lot of additional dust or distortion, or the appearance of dust or distortion within your image. That can, depending upon the alternate light source, depending upon the wavelength of the light that is being captured, that can have a complete impact or have a complete degradation of your ability to actually accurately visualize and analyze the different characteristics that you might have even with a footwear impression, because you can pick up enough noise that if you have a cast or if you have a footwear impression that is in dirt or sand, that the reflective nature of the background added to the noise of the sensor can create massive distortion in terms of trying to visualize that level of detail within the actual image itself.
Awesome. Well, thank you. I think we are about out of time, so we'll go ahead and start wrapping things up. I want to go ahead and first thank our subject matter expert for taking the time out of their day to present the material for today's webinar and answer all those questions. So thank you again, David, for taking the time. And we really appreciate you giving such a thorough overview of the topic.
Thank you very much. It's my pleasure indeed.
For everybody in the audience, David will be back this Thursday, just in 2 days, for another webinar related to digital imaging processing, specifically best practices for digital imaging processing. So that'll be this Thursday coming up, August 5th, same time, 1 p.m. Eastern. And we hope you come back around and join us for that.
All right, thank you so very much, Tom.
We would also like to take this time to thank our audience for joining us today. These webinars would not be possible without your attendance and support. Before you leave today's webinar, we would like to ask you to participate in a short survey. You can locate that link back on the webinar's main page. Simply click the word survey, and that will bring up our quick customer satisfaction survey for today's event. Your feedback about our webinars is vital information that we use to provide you with the best webinar experience and adjust the content and the way we disseminate the information to our audience. One more thing to draw your attention to, you should see we are putting links into the chat to all our social media pages, such as Facebook, LinkedIn, and Twitter, as well as a link to our website at forensiccoe.org and a link directly to our podcast episodes. Make sure you are following us on social media and subscribe to our newsletter to stay up to date with everything that FTCOE is doing in the forensic community. Thank you again for attending, and we hope everyone has a great rest of your day.